Okay, I didn't hear a beep, but I am recording and I've got audio, so hopefully it's recording. Here you go, Kenny. Start this going around the room. And I will see if I can reconstruct our problem. We have 7 degrees. Here. Boom. So, and the y direction, we're going to look for. See, where do we define 0? Oh, good morning, yeah, you. 0 at the top or at the bottom? Yeah, well, let's just say we're starting off at y sub naught is 0. So we're going to go to minus 1.5 meters is y. Okay, and then we've got 0 meters plus v sub naught y times t minus 1/2 of g is 4.9 times t squared. And the second one is 22 meters is equal to 0 plus v sub naught x times t plus 0, because the horizontal acceleration is 0 the instant he leaves the ramp. Now, v sub naught y is v sub naught times the sine of 7 degrees. V sub naught x is v sub naught times the cosine of 7 degrees. So we can rewrite these equations as minus 1.5 meters equals v sub naught y, which is v sub naught sine of 7 degrees minus 4.9 meters per second squared times t squared, and 22 meters is equal to v sub naught x, which is v sub naught cosine 7 degrees times t. And that's it. So, those are the 2 independent equations that we have describing the motion of this vehicle after it leaves the ramp. And they are both independent equations. So, the problem is how to solve them, because we have 2 unknowns. We need to know the time that the car is going to be in flight before it drops to minus 1.5 meters. We already solved the first part where it was left horizontally, and that was no problem. All we had to do was find the time it took it to fall, and then we used because there was no vertical component to its velocity. So this had no unknowns, only the one unknown in it. We solved for t. We used t to calculate how far it would go to find out what velocity, horizontal velocity it needed to go 22 meters in that amount of time. But now, it's going to take longer. T is no longer, it's going to be a little bit longer than it used to be because we now have this vertical component. We've got 2 unknowns that we have to solve for simultaneously. So, show of hands. Who has an idea how they would start? And I know I'm torturing you, but I'm doing this on purpose. I want you to struggle and to think, because I want you to remember this problem and how the solution really does work out. So somebody give me a guess. What could we do to solve these equations? And what, by the way, what we're doing is called solving them simultaneously. So does anybody have a guess? Okay. Is there any way we could make one of these equations so it only had one unknown in it? If we could make one of the equations with only one unknown, then we could solve for that unknown. But we can't solve a single equation for two unknown variables. So how about we do this? Let's take this second equation. 22 meters equals v sub naught cosine of 7 degrees meters per second times t seconds. So we've got meters per second cancels out with seconds. Meters equals meters. We're good there. If we divide both sides of that equation by v sub naught cosine of 7 degrees, we end up with 22 meters divided by v sub naught cosine of 7 degrees meters per second is equal to t seconds. And when we divide meters by meters per second, we end up with seconds on this side equals seconds on that side. So, we have just written time, t, as a function of v sub naught. I'm sorry, yeah. We've changed. Yeah, we have time now as a function of v sub naught. Yeah, I'm doing that backwards. I thought I was doing that backwards. How about instead, let's solve for v sub naught. If we divide both sides by cosine 7 degrees and time, we end up with 22 meters divided by cosine of 7 degrees times time equals v sub naught. Cosine of 7 degrees is unitless, because it's a trig function. Time is in units of seconds, so we have meters per second is equal to meters per second. But look what we have now. We have v sub naught as a function of time. Now let's plug this back into this equation and see what we get. We've got minus 1.5 meters is equal to v sub naught, which is 22 meters divided by cosine of 7 degrees times time. And this, you see, is v sub naught times cosine of 7 degrees. Oh, sorry. Wrong equation. Times sine of 7 degrees. Minus 4.9 meters per second squared times t squared. Let me clean that up. Now, who knows what sine divided by cosine is? No. Nope. Sine divided by cosine is tangent. So we can rewrite this now as minus 1.5 is 22 times tangent of 7 degrees minus 4.9 t squared. Now we can solve this for t. Tangent of 7 degrees is just a number. So we've got minus 1.5 minus 22 tangent of 7 degrees. That's 22 times the tangent of 7 degrees is equal to minus 4.9 times t squared. So we divide both sides by negative 4.9 and we get minus 1.5 minus 22 times tangent of 7 degrees divided by negative 4.9 is equal to t squared. Somebody with a calculator. Find minus 1.5 minus 22 times tangent of 7 degrees. Okay, then let's try that again. Negative 1.5 minus 22 times 7. Yeah, I think I left off the 22. Okay, I got a completely different answer that time too. Or did you already divide by 4.9? Okay. Well, let's do just the first one. 1.5 negative minus 22 times minus 4.20 divide that by minus 4.9. I wanted to make sure we did this step because I want you to see that we're dividing a negative by a negative, which gives us back a positive. Otherwise, if we ended up with a negative, we try to take the square root of it, we're getting off into imaginary numbers. We're not going there. So, now, minus 4.20 divided by minus 4.90, because we've got 3 digits there, is equal to what? Now let's keep for the 3 digits. 0.857. Wait, how many digits do we significant? We had 3 significant digits to begin with, didn't we, or 2? 2? Okay. And we'll do 8.6 is equal to t squared. And when we take the square root of it, .93 seconds. How many seconds was it in flight the first time? Now it's up to 0.93. So giving it even that slight vertical velocity gave it a whole lot more time. Well, now that we have the time, we can plug it in right here, and we've got v sub naught. So the time was what, 0.93? Well, let's see, 22 divided by 0.93 times the cosine of 7. gives you V sub naught. Who's got an answer? Okay, so we're going to go with 2 digits. 24 meters per second. And if I'm not mistaken, that was what the question asked for, was what velocity does it need to leave the ramp with? "24 meters per second at 7 degrees. Does everyone see how this was solved? When you have 2 equations and 2 unknowns, right? One of the unknowns, look at this equation. You've got t here and t here. V sub naught only shows up once. Where am I at? Here. Yeah, I left off the t here, didn't I? Oh, did that mess me up over here? I bet it sure did. Yep. Back up, folks. Did this mess me up? We solved this for t. Yeah, but I want to make sure I didn't. Yeah, well, that's not acceptable. V sub naught times sine of 7 times time right here, which would have canceled out this time. Yeah, but that's just careless, stupid luck. That's not. But yeah, you're right. Here's where I just accidentally fell back into the right answer. So do not take my example for that. Anyway, any questions? You've got 2 equations, 2 unknowns. Find one of the unknowns in terms of the other unknown, and you can then make the substitution, get back to a single equation with only one unknown that you can solve for, which will then allow you to go back and solve for the first unknown. That's called simultaneous solution. Now, for those of you who did not hear, we do have an exam on Monday. It'll be an in-class exam covering Chapter 3. So today I need to cover the topic of relative velocity, and then after that it's going to be review the material from Chapter 3, answer questions from the homework. So let me cover relative velocity very quickly, and we'll go from there. How many of you remember relative velocity from Chapter 2, where we were doing motion in 1 dimension? Anybody? Seriously? Nobody remembers relative velocities? 2 trains are headed at each other at 80 miles per hour each. How fast do the 2 trains appear to be going to observers on the ground? 80 miles per hour each. How fast does the second train appear to be going to people on the first train? No, they're coming at each other. 160 miles per hour. You're driving down the interstate at 75 miles an hour. The car in front of you is only doing 70 miles an hour. So you drive past them. How fast do you appear to be going to people in that car? 5 miles an hour. And as long as the motion, relative motion, is limited to a single axis, one dimension, then addition and subtraction is all you're going to need in order to find out, in order to deal with the relative velocities between the two. And we did look at an example where, I forget the problem now, but there was one problem we had where it was that was the whole issue. Was once you treated it as, once you stopped treating them as two separate motions and just one motion relative to the first, then the problem became very simple to solve. Now we're dealing with motion in 2 dimensions. So simple addition and subtraction is no longer sufficient. Now we're going to you have to deal with the vector sum of 2 relative velocities. Here's what we're talking about. Here is the banks of a river. Okay? This is a timely topic. We've got lots of rivers and lots of lakes all over the place these days. Now, you have a boat in the river. And the boat is pushing forward at 5 miles per hour. But that is relative to the water. What if the water is moving from west to east at 3 miles per hour? Now, what is the relative velocity of the boat? What is the velocity of the boat with respect to the shore? Well, that's an unfortunate combination. The velocity of the watercraft with respect to the shore. Go ahead. Let's find out. It's going to be the vector sum of the 2 velocities. Relative to the shore, the boat is moving 5 miles vertically with respect to the water and 3 miles per hour horizontally with respect to the shore. So the velocity of the boat, velocity of the watercraft with respect to the water is 5 miles per hour at an angle of 90 degrees. The velocity of the water with respect to the shore is 3 miles per hour at 0 degrees. We're going to add them together. The first thing we got to do is write them in rectangular coordinates. So this one in rectangular coordinates, velocity of the watercraft with respect to the water equals 0I plus 5 miles per hour J. Straight up. Velocity of the water, too many V's and W's in one sentence. The velocity of the water with respect to the shore is, and that's also going to be 3 miles per hour I plus 0 miles per hour J. The vector sum is now 3 plus 0 I plus 5 miles per hour J. And that is equal to the velocity of the watercraft with respect to the shore. There. All to avoid using boat. Now, that is the resultant vector velocity of the boat relative to the shore. Okay? However, we still want to put this in polar coordinates. So what's our magnitude of our velocity vector? Somebody. Anybody. How do we find the magnitude of this resultant vector? Pythagorean theorem. Thank you. 3 squared plus 5 squared. Take the square root. That's going to be 9 plus 25. Take the square root, which is, what's that, 34? And don't trust me for the arithmetic. Is it 34? Okay, what's the square root of 34? 5.83 miles per hour. Now, what is its angle? What's its direction relative to the shore? Very good. And that gives us, making certain you're in degree mode, (59 degrees). So the relative velocity of the boat to the shore is 5.8 miles per hour at an angle of 59 degrees. See, mathematically, it's the same as when we were working in one dimension. It's just the sum or the difference of the relative of the two velocities. But because we're in 2 dimensions, you have to do vector addition. Right? Is everybody signed in? That is, the velocity of the boat relative to the shore. Because the velocity of the boat initially is given relative to the water, and then the water is moving relative to the shore. So the boat relative to the shore is the vector sum of the 2 relative velocities. Somebody didn't sign in yet. Who's not signed in? Chris? Pass this back to Chris. Let's see, do they give any examples in the book that we can work through? Well, they did the one we just did. Huh. Everybody got this? Okay, well, that marks the end of the material in Chapter 3. And you all have an exam on the material in Chapter 3 bright and early Monday morning. So, now would be a really good time to ask questions. What part of the material in Chapter 3 do any of you want to go back and look at? Or what homework problems do you still have questions about? 48? Let's see. A boat whose speed in the water is 2.5 meters per second must cross a 285 meter wide river and arrive at a point 118 meters upstream from where it starts. To do so, the pilot must head the boat at a 45-degree upstream angle. What is the speed of the river's current? Okay, let's draw this out. The velocity of the boat relative to the water is 45 degrees. What velocity did they say? First of all, am I reading the right one? Okay. 2.50 meters per second. And we know that the distance across is 285 meters. The resultant path is 118 meters downstream or upstream. Yeah, because the river current is flowing this way. And that is unknown. That's what we've got to solve for. So, this boat is going 45 degrees at 2.5 meters per second. What will the angle of its final vector, of its net velocity be? So yeah, that's good. There we go. What we want to find out is, what is this angle here? The angle of the resultant actual velocity. We can find this angle as the inverse tangent of 118 over 285. Right? So what does that give us for this angle here? Somebody have a result? Say again. 22.5. And if this is 22.5, what does that mean this angle is? 90 minus 22.5. So this theta of the net angle of the trajectory of the boat is going to be 67.5 degrees. That means when we add 2.5, just so we're clear on what we're doing, when we add 2.5 meters per second at an angle of 45 degrees to the velocity vector of the current, the result is going to be the velocity, the net velocity of the boat plus the current at an angle of 67.5 degrees. Okay? Well, let's start by converting our velocity of the boat relative to the shore into rectangular components. Velocity of the boat relative to the shore is 2.5 meters per second at an angle of 45 degrees. In rectangular coordinates, that is 2.5 times cosine 45 I plus 2.5 sine 45 J. Now, what do those components work out to? You get 1.78, you get 1.77. Okay. 1.77 meters per second I plus, little known fact, at 45 degrees, cosine and sine are the same, so this is going to be the same. Now, what do we know? Okay, let's just to keep things straight, let's make sure we all know which vector we're talking about. We have the vector of the boat, which is the boat relative to the shore, which is this right here. We have the velocity of the current relative to the shore, which is unknown. And we don't have the velocity of the boat relative to the water, but we know that when we do, I'm sorry, that is the velocity. I wrote this as the velocity of the boat relative to the shore, and it is not relative to the shore. This is the velocity of the boat relative to the water. The velocity of the water relative to the shore, the water of the current relative to the shore, and the vector sum will be the net velocity of the boat. Okay? We don't know the magnitude of the velocity of the boat relative to the shore, but we know that it will be at an angle of 67.5 degrees. Okay? We also know that the velocity of the boat, the net velocity of the boat relative to the shore at 67.5 degrees is going to give us 118 meters after it has traveled 285 meters, which is how we got the direction. What is going on with my head this morning? But it ain't because I didn't have enough coffee. All right. Am I missing something? No, we've got to go 285 meters across and arrive at a point 118 meters. So we're going to have to subtract that component of the river current from that component of the we're going to have what would we subtract from 1.77 meters per second squared, because we know, okay, follow with me here. We know that the velocity of the current is going to be the velocity of the current relative to the shore, I, plus 0j. All right? There is no vertical component to the velocity of the current in the water. Does everybody see that? So that means that the vertical component of the boat's velocity relative to the shore is not going to change. Right? And yeah, see, this is, I can tell you now what it is that's throwing me here. It's because, I just want to erase this right here. This is I, and this is J. Now, this part of the boat's final velocity is not going to change. It is still going to be, it's still going to have the same vertical component, because the vertical component here is 0. What is going to change is the horizontal component of its velocity. It's going to lose this much relative velocity. So, I'm trying to phrase this in the form of a question that will make sense to you. We're looking for the inverse tangent of, which one's vertical and which one's horizontal. .77 divided by x will equal to 67.5 degrees. All right? Make sure I'm doing that right. No, I'm not. I'm still not doing it right. Because this angle is going to be 67.5 degrees. Tangent of that angle is going to be yes, it's still going to be this divided by the 1.77 divided by this. So if we solve that, what's the tangent of 67.5 degrees? .41 and x equals 1.77 divided by 2.41 equals 0.73. Does that make sense? We change the vertical component of the boat's velocity to 0.73, then that would equal the original horizontal component of 1.77 minus the current of the river. Relative to the shore. So 0.73 minus 1.77, we end up with minus 1.03 or minus 1.04 equals minus the velocity of the current relative to the shore. So that would give us the velocity of the current equals 1.04 at an angle of 180 degrees. Now, I have absolutely zero confidence that I have done this correctly, so let's test it and find out. We have, I'm not going to erase anything just in case. What we're saying is that a boat with a velocity relative to the water of 1.77 I plus 1.77 J and we add to that the velocity of the current, which would be minus 1.04 I plus 0J. We add those together, we end up with a net velocity of the boat relative to the shore. 1.77 minus 0.04 is 0.73 I plus 1.77 J, which gives us a magnitude. Well, without worrying about the magnitude, what does that give us for the angle? Inverse tangent of 1.77 divided by 0.73 equals 67.5 degrees. And the magnitude of the velocity of the boat then is 0.73 squared plus 1.77 squared. Take the square root of, and that gives us who else gets an answer? Good. And that's it. 1.91 meters per second at 67.5 degrees. And that does work out, because at 67.5 degrees, it will cross the river 118 meters upstream. Now, what this should give, what this should show you and demonstrate for you, at my expense, is that it's incredibly important to keep these vectors straight in your mind. What you're adding to what you're subtracting from what. Because they can get very, very confusing very quickly. So, draw pictures. Any more questions? Everybody ready for Monday? Yeah, I wouldn't hold my breath for that. There might be a relative velocity problem on there, but my problem with the relative velocities are not that confusing when you've got everything. My problem is I'm trying desperate, when you have the boat relative to the shore, you end up with the subscript of BS, and I just don't like doing that. So keep them straight, and it's not that hard. It's not difficult, but thank you, Megan. But it can be complex. It can be complicated if you don't keep it straight.